Okay, so the next topic that I want to talk about is this, is the normal curve and a theorem known as the central limit theorem, which we're going to use in the remainder of this course. And so first I want to talk about the normal distribution. And here is the formula. It's a beautiful formula, but we will not use it at all from there. We'll use the results from it and we'll look at pretty pictures of it. But in case you know, Vassar is famous for going to the source, this is the equation that generates this standard normal curve. And what does it look like? So this is the classic bell curve from there. And so kind of a couple of properties about it. So one, you can see that it is centered. It is centered at 0. So its mean is 0. Z, right? So Z, so this is in standard units. So this is where my mouse is 1 standard unit, 2 standard units, 3 standard units, and so on and so forth from that, right? You can think of this normal curve as a distribution as a histogram. And so the area under this curve, so area under this entire curve is going to be 1. And it's symmetrical. It's symmetrical around 0. And we can see that from there. Okay. And so one other thing too that's kind of worth pointing out, just kind of looking at the quality of it, is that after a while you might be, by looking at kind of normal distributions, and we've seen normal distributions come up in the data that we've looked at in nature. Sometimes like height distributions tend to be normal, and we've looked at it as the results of running some of our random sampling simulations. And so notice that kind of at the 1 standard deviation mark, right? There's this point of inflection. And the way kind of the book describes it, I think it's kind of helpful, is that if you kind of look at the area in between plus and minus 1, it's, the area plus and minus 1, it looks like kind of an upside down cup, right? And then if you look at this area from 1 and beyond, the cup is now kind of inverted, right? So it's between minus 1 and 1, it's kind of an upside down cup. And then there's this point of inflection where it kind of starts changing from sloping, it changes the slope to now kind of being this gradual kind of curve from there, right? So this point of inflection happens at the 1 standard unit, 1 standard deviation from the center from there. Okay, so what is special and what is so magical about the bell curve is if we can say that a distribution is normal, right? We can now have some tighter bounds than Chebyshev's inequality. And so no matter, so basically, if we don't know the shape of the distribution, we rely on Chebyshev's inequality, which is the data is, plus or minus a few standard deviations from the data. However, if we know that it is bell-shaped, it's a normal distribution, we can now go from, instead of saying most of the data is within, a few standard deviations, now we can say almost all of the data, and we're talking 99.7% of the data, okay? Almost all of the data is in the range of plus or minus 3 standard deviations. That is a much, much tighter bound than Chebyshev's inequality, right? We saw, 96% of the data is in plus or minus 5. Now we're saying virtually all, 99.7 is within 3 standard deviations of the average, okay? And so kind of visualizing this in happy chart form, you can see that if we know the distribution is normal, we can have much tighter bounds, right? So within 2 standard deviations, just relying on Chebyshev's, as we saw, we know 2 standard deviations, we got about 75% of the data. If we know the distribution is normal, now we've reached our magic number of 95%. From there. And drawing out the bounds to plus or minus 3, right? That gives us, just for any old distribution that we don't know anything about, it's like 89%. Here, virtually all of it, 99.73% of that from there, okay? So if we know that the distribution is normal, we can say a lot more about where the bulk of the data lies. We have much tighter bounds. Otherwise, we have to just fall back on Chebyshev's inequality from there, okay? And so kind of tying it now to when we started kind of thinking about these interval ranges, right? Now we can say within plus or minus 2 standard deviations of our median, right? So you can see here, so we're here, and then if we go out, shown in yellow, out 1, out 2 on both sides, that's going to cover 95% of the area. So 95% of the data is going to lie within 2 standard deviations of the average from there. Okay. So how do we kind of put this in practice? Well, the good news is that we see in nature, there are a lot of normal distributions. And so I've kind of shown the actual histogram of from our birth table, the birth weight in kilograms, and I've superimposed over that the normal curve for that. And you can see the two track, fairly closely to that. It happens in things like shoe size, right? Heights of men and women also follow this normal distribution. And as crazy as things as length of deer antlers, right? It just pops up all the time in nature. And where does it come from, and how do we make use of this? This comes down from this technique of the central limit theorem. Okay, and this is also the second reason why we're going to use the standard deviation for computing variability. And so what the central limit theorem says. So if we're taking a sample from a population, if that sample is large and drawn at random with replacement, okay, regardless of the distribution of the population. So regardless of what the actual distribution of the population is, the probability of the distribution sum or sample average, okay? And really this is the two kind of, kind of can go related because, right, the sum of all the samples divided by the length of the sum is just the average, right? So you can think of this, the average is just the sum divided by some constant factor. So regardless of the distribution of the population, so the sample average is going to be roughly normal, okay? And let me, again, this is the sort of thing where the demo will kind of drive this point home and kind of seeing that. So again, while I'm kind of setting up this demo, any questions? Okay, let's see this in practice. All right, so we're going to go back. We're going to go back to our flight delays, our flight delay data. And so if you remember, so this is our flight delay data, and here's the histogram of that. And so if you remember, we're measuring the delay in flight departures in minutes. And this is the distribution of flight times, right? You can see it's kind of tails off, and it is definitely not a normal distribution, right? From there. And so if we take a look at that, and we can compute, right? So we can compute the average delay. We can compute the average delay, and that's about 16.6 minutes from there. And we can compute the standard deviation. And so notice that the standard deviation is quite large compared to the mean, right? The mean is about 16, but the standard deviation is almost 40. And you can see that, you can see this by this tail. You can see this by how it has, like, this distribution has a very long tail. And the way, I kind of like to think of it is that the data that is further away from the mean, even though there's not a lot of it, right, relative to there, the data that's further away is pulling. You can think of that as these outlying data, these large delays are pulling the standard deviation away from the mean from there. Okay, and so, you know, even though there's not a lot of them, but because the delay is so large, you know, like they maybe had to replace a part on the plane and you were sitting on the tarmac for like 2 hours, you know, that has it has an impact on the variability, on the standard deviation. And if you remember too, right, this kind of drives home the point that there is definitely a difference between the mean and the median, right? Because if we look at the 50th percentile, the median, we saw that half of the flights had a delay of less than 2 minutes, which is good news for, you know, for people who fly a lot from there. Okay, so that's just a review of our data. And so now what I want to do is just write a little helper function to calculate from a sample size. So remember, in this flight data, we have the population data. So we have all of the data. This is kind of our go-to data when we have all of the population data. Okay, and so what we're going to do here is we'll just write a little helper generic function that will calculate one statistic, one sample mean from any given sample size. Okay, and how do we do that, right? It's the same thing that we've been doing for weeks now. We're going to take a sample from our sample size without replacement, and then that's going to be our sample flights, and then we're just going to compute the statistic on our delay column from there. Okay, so we're taking our random sample, and then we're just computing our statistic, which in this case is just going to be the mean. Okay, so now that we have that, we can run for any sample size that we want. So if we just run it with a sample size of 100, we'll see that every time we run it, we're going to get a different value from there. And you can see that, you know, they're not too far away from our median, our mean rather, which is around 16.6. Okay, but we know because it's random, you know, we're going to get some variation across that. So now let's create another helper function that instead of just doing it once, we're going to do it 10,000 times. Okay, we're going to do it 10,000 times. And get a sense of the distribution of these 10,000 values. So each one of these trials is going to be grabbing a sample from our population and computing the statistic on that. And so our sample size, again, we can pass in as a parameter, but then whatever that is, we're going to do that 10,000 times to get us our distribution. And so from here, so we'll call our 10,000 sample means, right, with and each time we're going to be drawing a random 100. That's our sample out of the population. So we run that, and it's going to take a little bit of time to run because each one of these trials. Okay, but that's not too bad. And if we take a look at that, we're going to get an array. How many elements are in this array? Anyone?
100.
Well, let's take a look.
Or 10,000.
10,000. And so the 100 comes in, and the 100 is very important. The 100 comes into the population that we're drawing from our sample size. So I think it's easy to get mixed up, which is kind of why I asked that question. So we're going to do 10,000 trials, and each trial we're going to draw 100 members from our population from there. So now that we have our 10,000, right, we can see, we take the length, we get it, and now we're going to get a distribution. We're going to get our distribution, and if you remember, our population average was 16.6, all right, and this is the known quantity. This is ground truth from that, because we have the entire population for this example, but we can see from the distribution, right, of these 10,000 random samples of 100, you can see that what does the actual distribution of this statistic is normal shaped, is normal, right? It looks very much, it's not perfect, but it is definitely very normal shaped. And where is it centered? It's centered right around roughly our population average, okay? So this distribution of the statistic that we calculated from this random sample of 100, 10,000 times is normal. Our original population data is not a normal distribution, right? It is kind of this one-sided tail distribution. And that comes down to the exact tenet of the central limit theorem is that if we do a large enough random sample of a population, regardless of the distribution of the population, which is this right here, regardless of the distribution, our results are going to be normal with the mean, with the distribution centered around the population mean from there. Okay, and that's exactly what the central limit theorem is gonna tell us. All right, so now that we have this helper function, we can now actually look at how does the shape of our distribution vary with the sample size. So we're still to compare our distributions, we're still gonna run 10,000 times. We're gonna run 10,000 times, but the one parameter that we're gonna change is the sample size. So instead of pulling 100 pieces of data from our population, we're going to do more surveys. So this example here, we're going to pull 400. Okay, and so if we run 400, now we get a normal distribution. We get a normal distribution. Again, it's centered kind of roughly around the population average, the ground truth. But look at what happened, right? And this is it's a little hard to see this because of the way that the histogram, right, kind of already picks its labels. But I want you to look at kind of the tail of the distribution between the two of these, okay? Again, both of them are centered roughly around the population average. But look at the tails, right? Look at the tail of the 100 sample one, right? It kind of goes out to just about 30, and it's, maybe like around maybe like 6 or so, from 6 to actually 30, right? There is actually a little bin from down there. But now if you look at when we sampled 400, what happened to the range, right, or the variance of our distribution? It got a lot smaller. Look at the tail. Look at the tail before. Here it's out to 30. Now it's 22.5. And here it was like 6, and here it is over 10. And so what happened? It's still centered around our average, but the variance, how far away we are from the population average, it got a lot narrower. Like the shape of the bell curve got squished. It got squished from there. Okay, and so kind of just rounding this, driving this whole point home, let's try one more. Let's run it with 900 samples. 900 samples, and we see the exact same thing. Our bell curve, our normal distribution, has gotten a lot tighter. Not as drastic as before, right? From here, it went from 30 to 22.5. So that's interesting. And it got a little smaller. It got, to maybe like 21. In the bounds. So that's interesting, right? We'll come back to this point. We increased by more than double, 400, and our bound definitely got a little more narrow, but it got less narrow. So this the intuition here is that there's two kind of takeaway intuitions from this demo that I want you to kind of come away with. One is that as we increase the sample size, from our population, the distribution, our variance around the average gets tighter. As we increase, we're basically honing in, we're narrowing in, we're getting a smaller variance around the average. And there seems to be some kind of sense of diminishing returns. As the sampling is going up, we're getting narrower, but it's getting kind of less and less narrow from there. So there might be a limit. There might be a limit to how much sampling can narrow the standard deviation of our distribution. Okay, so those are kind of the takeaways from that. Any questions? Saying shaking heads, and that's a good case, right? Shaking heads is no in this case. From there. Good. All right, so let me stop this recording.